Hello everyone. My topic for presentation is attributes of graphics primitives. The topics which I'll be going through are color and grayscale, line attributes, line style, pen and brush options, curve attributes, fill area attributes, scanline polygon fill, scanline fill methods, wireframe methods, character attributes, and anti-aliasing. The most basic attribute for all primitives is color. The various color options which can be made available to a user depends on the capabilities and design objectives of a particular system. In a color raster system, the number of color choices available depends on the amount of storage divided per pixel in the frame buffer. The color information can be stored in the frame buffer in two ways. We can store RGB color codes directly in the frame buffer, or we can put the color codes into a separate table and use the pixel locations to store index values referencing the color table entries. A minimum number of colors can be provided in this scheme with 3 bits of storage per pixel as shown in the table. The leftmost bit controls the red gun, the middle bit controls the green gun, and the rightmost bit controls the blue gun. Adding more bits per pixel to the frame buffer increases the number of color choices we have. With 6 bits per pixel, 2 bits can be used for each gun. This allows 4 different intensity settings for each of the 3 color guns, and a total of 64 color options are made available for each screen pixel. With a resolution of 1024 by 1024, a full color RGB system needs 3 MB of storage for the frame buffer. So coming to color tables. Color tables are an alternate means for providing extended color capabilities to a user without requiring large frame buffers. Traditionally, this was an important consideration, but today, hardware costs have decreased dramatically and extended color capabilities are fairly common, even in low-end personal computer systems. The figure illustrates a possible scheme for storing color values in a color lookup table or a color map. The color table is also referred to as a video lookup table. A value of 196 stored at pixel position references the location in this table containing the hexadecimal value. Each 8-bit segment of this entry controls the intensity level of one of the 3 electron guns in the RGB monitor. A color table is useful in a range of applications. This is so because it can provide simultaneous colors without requiring any large frame buffers. Moreover, the table entries can be changed at any time, allowing a user to experiment with different color combinations in a design, scene, or graph without changing the attribute settings for the graphics data structure. Without a color table, we can only change the color of a pixel by storing the new color at that frame buffer location. Some other applications include data visualization applications, which can store values for physical quantities like energy, pressure in the frame buffer and use a lookup table to experiment with various color combinations without changing the pixel values. In visualization and image processing applications, color tables are used for setting color thresholds such that all pixel values above or below a specified threshold can be set to the same color. Grayscale. We use RGB color functions to shed shades of gray are called as grayscale in an application program. Grayscale image has each of its pixels as a single sample. When an RGB color setting specifies an equal amount of red, green, and blue, the result is some shade of gray. The values which are close to 0 for the color components produce dark gray, and higher values near 1 produce light gray. Applications for grayscale display methods include enhancing black and white photographs and generating visualization effect. In addition to an RGB specification, the other 3 component color representations are useful in computer graphics applications. For example, color output on printers is described with cyan, magenta, and yellow color components, and color interfaces sometimes use parameters such as lightness and darkness to choose a color. Traditional grayscale monitors showed up to 4 different shades, whereas today's monitors allow 256 different intensities. Some image formats which can support the 16-bit grayscale are TIFF and the PNG image formats. Dynamic range of common dividers. A 2010 computer display had between 1 million to 1.5 million pixels. A monitor's dynamic range is about 500. which means that the brightest pixel emits 500 times the energy emitted by the darkest pixels. And some of the devices listed below are the following: the LCD, negative field, human eye, which have the contrast and stops correspondingly. And coming to the characteristics of the human eye. Human eye has an angular resolution of about 1 minute of arc. This can be related to about 300 mm distance at 1 km distance. The human eye cannot differentiate between the pixels if they become half as large as their nerve. So, a 1 pixel position of single character on a line of text is completely unnoticeable. The human eye is very sensitive to motion, so two adjacent pixels in a gray region that alternately flash white gives an illusion of motion. Thereby, the user becomes more attentive. The eye's resolution from the center of the view is much less, which results in wastage of the pixel density that is present at the edge of the screen. Coming to line attributes. We can describe any line segment with three attributes. They are color, width, and style. The line color can be set with the same function, whereas the line width and line style are selected with separate line functions. If a line has a slope magnitude less than or equal to 1, we can modify a line drawing routine to display thick lines by plotting a vertical span of pixels in each column, that is, x position along the line. The number of pixels to be displayed in each column is set equal to the integer value of the line width. In the figure below, we display a double width line by generating a parallel line above the original line path. At each x sampling position, we calculate the corresponding y coordinate and plot pixels at the screen coordinates. We could display lines with a width of 3 or greater by alternately plotting pixels above and below the single width line path. This figure shows a raster line with a slope m greater than 1 and which has a line of width 4 plotted using horizontal pixel spans. Thick lines as offsets. We can adjust the shape of the line ends to give them a better appearance by adding line caps as shown in the figure below. We have three types of caps: the butt cap, round cap, and the projecting square cap. The butt cap has square ends that are perpendicular to the line path. If the specified line has slope m, the square ends of the thick line have slope -1 by m. The round cap is obtained by adding a filled semicircle to each butt cap. The circular arcs are centered at the middle of the thick line and have a diameter equal to the line thickness. Projecting square cap simply extends the line and adds butt caps that are positioned 1/2 of the line width beyond the specified endpoints. Some problem with implementing the width options using horizontal or vertical pixel spans is that the method produces lines whose ends are horizontal or vertical regardless of the slope of the line. Next, coming to three methods which can join two line segments: a mitre join, a Roy join, and a Weibull join. A mitre join is accomplished by extending the outer boundaries of each of the two line segments until they meet. A round join is produced by capping the connection between the two segments with a circular boundary whose diameter is equal to the line width. And a Weibull join is generated by displaying the line segments with butt caps and filling in the triangular gap where the segments meet. If the angle between two connected line segments is very small, a mitre join can generate a long spine that distorts the appearance of the polyline. Line styles. The line style attributes include solid lines, dashed lines, and dotted lines. Raster line algorithms display line style attributes by plotting pixel spans. For dashed, dotted, and dot dash patterns, the line drawing procedure outputs of contiguous pixels along the line path, skipping over a number of intervening pixels between the solid spans. Pixel counts for the span length and the interspan spacing can be specified in a pixel mask. Pixel mask is nothing but which is a pattern of binary digits indicating which positions to plot along the line path. For example, the linear mask this is used to display of a dashed line of dashed length of 5 pixels. Plotting dashes with a fixed number of pixels results in unequal length dashes for different line orientations, as shown in the figure. Both dashes shown are plotted with 4 pixels, but the diagonal dash is longer by a factor of 2. But we can display approximately equal length dashes by reducing the diagonal dash to 3 pixels. Another method for maintaining dash length is to treat dashes as individual line segments. The endpoint coordinates for each dash are located and passed to the line routine, which then calculates pixel positions along the dash path. The pen and brush options. Pen and brush options include shape, size, and pattern for the pen or brush. Some of the shapes are shown in the figure, which are stored in the pixel mask. A rectangular pen could be implemented with the mask, as shown. Moving the center of the mask along the line path, as shown is this one. The rectangular pen in this could be narrowed with the 2x2 rectangular mask or widened with the 4x4 mask. The lines can be displayed with selected patterns by superimposing the pattern values onto the pen or brush mask. Like you can see here, the various options, the sizes, and the patterns are different. This is a certain pattern. These are the sizes of the pen or the brush which can be used to draw any line segments. Next, the curve attributes. Parameters for curve attributes are the same as those for straight line segments. We can display curves with varying colors, widths, dot dash patterns, and available pen or brush options. The methods which are adapted for curve drawing algorithms to accommodate attribute section selections are similar to those for line drawing. The raster curves of various widths can be displayed using the method of horizontal or vertical pixel spans. If the magnitude of the curve slope is less than or equal to 1, we plot vertical spans, or if the slope magnitude is greater than 1, we plot horizontal spans. This figure shows the method for displaying a circular arc of width 4 in the first quadrant. Using circular symmetry, we generate the circle path with vertical spans in the first octant, that is from x is equal to 0 to x is equal to y. The circle sections in the other quadrants are obtained by reflecting pixel positions in the first quadrant about the coordinate axis. The thickness of curves displayed with this method is again a function of curve slope. Circles, ellipses, and other curves will appear thinnest where the slope has a magnitude of 1. We have another method for displaying thick curves, that is, to fill in the area between two parallel curve paths, whose separation distance is equal to the desired width. We can do this by using the specified curve path as one boundary and setting up the second boundary either inside or outside the original curve path. This approach, however, shifts the original curve path either inward or outward, depending on which direction we choose for the second boundary. An example of this approach is shown in this diagram, which has a circle segment with radius 16 and a specified width of 4. The boundary arcs are then set at a separation distance of 2 on either side of the radius of 16 to maintain the proper dimensions of the circular arc. We should set the radii for the concentric boundary arcs at 14 and 17. Though this method is accurate for generating thick circles, it provides only an approximation to the true area of other thick curves. Like for example, the inner and outer boundaries of a fat ellipse generated with this method do not have the same profile. The pixel masks discussed for implementing line style options could also use in raster curve algorithms to generate dashed or dotted lines. The following mask produces a dashed circle as shown in this figure. We can also replicate a pen shape along the line path for a circular arc in the first quadrant. Here, the center of the rectangular pen is moved to successive curve positions to produce the curve shape as shown in this figure. Painting and drawing programs allow pictures to be constructed interactively by using a pointing device such as a stylus and a graphics tablet, to sketch various curved shapes. Examples of such curved patterns are these. We also have an additional pattern option that can be provided in the Paint package, which is the display of simulated brush strokes. Some patterns that can be produced by modeling different types of brush strokes are the following patterns. You can see here that there are a variety of patterns which are modeled through the brush strokes. There are two basic methods for filling an area on raster systems. The first method is to determine the overlap intervals for scan lines that cross the area. Then pixel positions along these overlap intervals are set to the fill color. Another method for area filling is to start from a given interior position and paint outwards pixel by pixel until we encounter the specified boundary conditions. The scanline approach is usually applied to simple shapes such as circles or regions with polyline boundaries, and general graphics packages use this fill method. Fill algorithms that use a starting interior point are useful for filling areas with more complex boundaries and in interactive systems. A basic fill area attribute provided by a general graphics library is the display style of the interior. We can display a region with a single color or a specified fill pattern, or in a hollow style by showing only the boundary of the region. These three fill styles are illustrated or are shown in the figure. The first one is the hollow, the second the solid, and the third one is the patterned. For polygons, you could show the edges in different colors, widths, and styles. You can also select different display attributes for the front and back faces of a region. Fill patterns can be defined in a rectangular color arrays that list different colors for different positions in the array. A fill pattern could be specified as a bit array that indicates which relative positions are to be displayed in a single selected color. An array specifying a fill pattern is a mask that is to be applied to the display area. Some graphics systems provide an option for selecting an arbitrary initial position for overlaying the mask. From this starting position, the mask is replicated in the horizontal and vertical directions until the display area is filled with non-overlapping copies of the pattern. This process of filling an area with a rectangular pattern is called tiling. The rectangular fill pattern is sometimes referred to as a tiling pattern. Predefined fill patterns are available in a system such as the hatch fill patterns as shown in this figure. Hatch fill could be applied to regions by drawing sets of line segments to display either single hatching or cross hatching. Spacing and slope for the hatch lines could be set as parameters in a hatch table. Alternatively, hatch fill can be specified as a pattern array that produces sets of diagonal lines. We can combine a fill pattern with background colors in various ways. A pattern could be combined with background colors using a transparency factor that determines how much of the background should be mixed with the object color, or we can use a simple logical or replace operations. The figure demonstrates how logical and replace operations would combine a 2x2 fill pattern with a background pattern for a binary system, that is, a black and white system. Some fill methods using blended colors have been referred to as soft fill or tint fill algorithms. One use for these fill methods is to soften the fill colors at object borders that have been blurred to anti-alias the edges. Another application of a soft fill algorithm is to allow repainting of a color area that was originally filled with a semi-transparent brush, where the current color is then a mixture of the brush color and the background colors behind the area. In either case, we want the new fill color to have the same variations over the area as the current fill color. Next, scanline polygon fill. A scanline fill of a region can be done by determining the intersection positions of the boundaries of the filled region, the screen scanlines. Then the fill colors are applied to each section of a scanline that lies within the interior of the filled region. The scanline fill algorithm identifies the same interior regions at the odd-even rule. This figure illustrates the basic scanline procedure for a solid color fill of a polygon. For each scanline that crosses the polygon, the edge instructions are sorted from left to right, and then pixel positions including each intersection pair are set to the specified fill color. In this figure, the 4 pixel intersection positions with the polygon boundaries define 2 stretches of interior pixels. Thus, the fill color is applied to the 5 pixels from x equal to 10 to 14 and x equal to 18 to 24. If a pattern fill is to be applied to the polygon, then the color for each pixel along the scanline is determined from its overlap position with the fill pattern. Whenever a scanline passes through a vertex, it intersects 2 polygon edges at that point. But in some cases, this can result in an odd number of boundary intersections for a scanline. That case is this figure. Let me explain this. This shows 2 scanlines that cross a polygon fill area and intersect a vertex. The scanline Y intersects an even number of edges, and the 2 pairs of intersection points along the scanline correctly identify the interior pixel spans. The scanline Y' in fact intersects an even number of edges, but scanline Y intersects 5 polygon edges. To identify the interior pixels for the scanline Y, we must count the vertex intersection as only one point. Thus, as we process scanlines, we need to distinguish between the cases. Coherence properties are those properties where one part of a scene are related in some or the other way to the properties in other parts of the scene. To determine fill area edge intersections, we can set up incremental coordinate calculations along any edge. This figure shows 2 successive scanlines crossing the left edge of a triangle. The slope of this edge can be expressed in terms of the scanline intersection coordinates, where m is equal to yk plus 1 minus yk by xk plus 1 minus xk. Since the change in y coordinates between these 2 scanlines is simply yk plus 1 minus yk, the x intersection value on the upper scanline can be determined from the x intersection value on the preceding scanline as xk plus 1 is equal to xk plus 1 into the reverse 1 by m, that is, the m is the slope. Each successive x-intercept can thus be calculated by adding the inverse of the slope and rounding to the nearest integer. Thus, along an edge with slope m, the intersection xk value for scanline k above the initial scanline can be calculated as xk is equal to x naught plus k times inverse of the slope. In a sequential fill algorithm, the increment of x values by the amount 1 times of inverse slope along an edge can be accomplished with integer operations by recalling that the slope m is the ratio of 2 integers, where m is nothing but delta y by delta x, where we have that delta x and delta y are the differences between the edge endpoint of x and y coordinate values. Thus, the incremental calculations of x-intercepts along an edge for successive scanlines can be expressed as xk plus 1 is equal to xk plus the inverse of the slope, that is delta x by delta y. Scanline fill of convex polygons. A convex polygon has all its interior angles less than 180 degrees. The vertices of the polygon will point outwards away from the interior of the shape. We need to process the polygon edges until we have 2 boundary intersections for each scanline crossing the polygon interior. We use the coordinate extents to determine which edges cross a scanline. Intersection calculations with these edges determine the interior pixel span for that scanline, where any vertex crossing is counted as a single boundary intersection point. Some graphics packages further restrict fill areas to be triangles. This makes filling even easier because each triangle has just 3 edges to process. This is the scanline algorithm. The algorithm works by intersecting scanline with the polygon edges and fills the polygon between pairs of intersections. First, we need to find out the ymin and phi maximum from the given polygon. Then the scanline intersects with each edge of the polygon from the minimum value to the max. Next, sort the intersection point in the increasing order of x coordinates, that is from the P0, P1, P1, P2 and P2, P3. Finally, we have to find all those pair of coordinates that are inside polygons and ignore the alternate pairs. Coming to the scanline fill methods, we have the boundary fill algorithm, the flood fill algorithm, the 4 connected and the 8 connected. When the interior of a region is specified in a single color pixel until we reach the boundary, this is known as boundary fill algorithm. In this figure, the 4 neighboring points are tested. These are the pixel positions that are right, left, above and below the current pixel. Areas filled by this method are called 4 connected. The second method, as shown here, is used to fill more complex figures. The set of neighboring positions which need to be tested include the 4 diagonal pixels as well as those in the cardinal directions. Fill methods using this approach are called 8 connected. An 8 connected boundary fill algorithm would correctly fill the interior of the area as shown here, but a 4 connected would not fill the area completely. This is the pseudocode for an 8 connected region boundary fill, where this is similar to a 4 connected, but the only addition we have is that the diagonal positions need to be tested. So we include the x plus or minus 1 and the y plus or minus 1. Recursive boundary fill algorithms may not fill regions correctly if some interior pixels are already displayed in the fill color. This occurs because the algorithm checks next pixels both for boundary color and for fill color. Encountering a pixel with the fill color can cause a recursive branch to terminate, leaving other interior pixels unfilled. To avoid this, we can first change the color of any interior pixels that are initially set to the fill color before applying the boundary fill procedure. We can also fill an area that is not defined within a single colored boundary. That is, we can paint areas bordered by several different colors by replacing a specified interior color instead of searching for a particular boundary color. This fill procedure is known as flood fill procedure or the flood fill algorithm. We start from a specified interior point and reassign all pixel values that are currently set to a given interior color with the desired fill color. If the area we want to paint has more than one interior color, we can first reassign pixel values so that all interior points have the same color. This is a figure which shows an area with multiple color boundaries. Using either a 4 connected or 8 connected approach, we can step through pixel positions until all interior points have been repainted. The following procedure fills a 4 connected region recursively starting from the input position. We can modify this procedure or the algorithm to reduce the storage requirements of the stack by filling horizontal pixel spans for the boundary fill algorithm. In this approach, we stack only the beginning positions for this pixel spans having the value interior color. Starting at the first position of each span, the pixel values are replaced until a value other than interior color is encountered. Next, the full connected polygon. The algorithm basically follows the following steps. First, we have to initialize the value of seed point, the F color, the D color, the diagonal color, and the face colors. Define the boundary values of the polygon. Next, we need to check if the current seed point is default. Then, we need to repeat the steps. Change the default color with the fill color at the seed point. Then the following procedure with the neighboring 4 points is followed. But the drawback of this full connected technique is explained with this. If we try to fill this entire region by this algorithm, we may not be able to fill this area. This is overcome by the 8 connected technique, where we also put pixels in diagonals so that entire area of the pixel is covered. So this area won't be, or it will be filled with the 8 connected, which is not the case with the 4 connected. And the algorithm for the 8 connected polygon is similar to that of the 4 connected polygon. First, initialization is done and check if the current seed point is of the default color. Then you have to repeat this steps. Next, change the default color with the fill color at the seed point. Then this procedure with the 4 neighboring points is recursively followed to fill these area completely. The wireframe methods help in choosing only the polygon edges, where a wireframe or a hollow display of the polygon is produced. You can also display a polygon by only plotting a set of points at the vertex positions. These options are selected with the following function. The parameter face is used to designate which face of the polygon we want to show as edges only or the vertices only. Then this parameter is assigned either the front face or the back face or the front and back. Next, if we want only the polygon edges displayed for a selection, we assign the constant the line to parameter display mode. To plot only the polygon vertex points, we assign the constant point to the polygon points to display to the parameter display mode. There is also a third option available that is used to fill. This is the default display mode, so we usually invoke the polygon mode when we want to see set attributes for the polygon edges or the vertices. This can be done by specifying the polygon twice, once with the parameter display mode, which is set to fill, and then again with display mode, which is set to line at the point. For a 3-dimensional polygon, this method for displaying the edges of a fill polygon may produce gaps along the edges. This effect is known as stitching, which is caused by differences between calculations in the scanline fill algorithm and calculations in the edge line drawing algorithm. As the interior of a 3-dimensional polygon is filled, the depth value is calculated for each position, that is the xy coordinates. Therefore, when visibility tests are made, the interior fill color could be used instead of an edge color to display some points along the boundary of polygon. And one way to eliminate the gaps along display edges of a 3-dimensional polygon is to shift the depth values calculated by the fill routine so that they do not overlap with the edge depth values for that polygon. This can be done with the following 2 open functions, which enables and the polygon offset. The first function activates the offset routine for a scanline filling, and the second function is used to set a couple of floating point values that are used to calculate the amount of depth offset. This is the basic idea of wireframe methods. Next, character attributes. The character attributes are generally considered to be the font, size, color, and orientation. The choice of font for a character varies as there is a particular design style, such as New York, Times New Roman, Cambria, Calibri, etc. Also, the characters can be in bold, italic, or any shadow styles. The color settings for displayed text can be stored in the system attribute list. This is used by the procedures that generate character definitions in the frame buffer. When a character string is to be displayed, the current color is used to set pixel values in the frame buffer corresponding to the character shapes and positions. We could also adjust text size by scaling the height and width of characters, as shown here. This is height and width, both are manipulated, whereas here the width is manipulated. This is the vertical and the horizontal arrangement of characters in a line of text or a string, and this is the spacing which is used to differentiate between the characters. We can also change the orientation for a character string. The orientation for a character string can be set according to the direction of a character up vector. So if the up vector increases by 45 degrees, the resulting text would be like this, and the XY plane of 45 degrees. A procedure for orienting text could rotate characters so that the sides of character bodies from brace line to cap line are aligned with the up vector. The rotated character shapes are then scan converted into the frame buffer. So these are the general attributes of characters. Next, anti-aliasing. The distortion of information due to low frequency sampling is called aliasing. This can be overcome, and we can improve the appearance of displayed raster lines. That is, the undersampling can be negotiated or compromised by applying anti-aliasing methods that can compensate for the undersampling process. An example of the effects of undersampling is as shown in this figure. Here, each square pixel area is divided into 9 equal sized square subpixels. The shaded regions as shown in and this is talking about this figure, and the shaded regions show the subpixels that would be selected by the Bresnel's algorithm. This provides for 3 intensity settings above 0, since the maximum number of subpixels that can be selected with any pixel is 3. The pixel position at 10,20 is set to the maximum intensity, that is at level 3. Pixels at 11,21 and 12,21 are set to the next highest intensity of level 2, and the pixels at 11,20 and 12,22 are each set to the lowest intensity, that is at level 1. Thus, the line intensity is spread out over a greater number of pixels to smooth the original jagged effect. Now, if we take the finite width of the line into account, we can perform supersampling by setting pixel intensity proportional to the number of subpixels inside the polygon representing the line area. A subpixel can be considered to be inside the line if its lower left corner is inside the polygon boundaries. An advantage of this supersampling method is that the number of possible intensity levels for each pixel is equal to the total number of subpixels within the pixel area. As shown in this figure, we can represent this line with finite width by positioning the polygon boundaries parallel to the line path shown in this figure. Each pixel can now be set to one of 9 possible brightness levels, that is above 0. That's it. Coming to the references, these are the references which helped me in doing the PPT. And thanks everyone for your patience and watching my video. Thanks a lot.